How are you today?
Good, how are you?
Good. I'm doing very well. Thank you. I have a new grandbaby on the way, and I just found out it's a boy. So that's fun. They already have a girl. So now they'll have one of each.
Congratulations.
Thank you. It's very exciting. Always fun when new babies come into the world. All right. Give me just 1 second here, everybody. All right. Terrific. Thank you all for coming. It's wonderful to see everyone. Anybody have any questions about the material from last week? Or anything that you're doing? I know we kind of jump in with, like into the deep end of the pool with physical science. A lot of times, physical science covers topics that are a little more um, abstract, I guess is a good word. Where when you're talking about biology, even chemistry, even some of that is more stuff that you deal with on a daily basis. Certainly, biology is. We live in the world of living things after all. But with physical science, it can be a little bit more difficult to figure things out because it's not things that you can see. We're dealing with tiny little microscopic things. All right. I'm going to remove the other one, Cheyenne. I think I can take that out. Yeah, I'll take that out.
If you hit the remove button, I think that the same account can never join the meeting ever again.
Really?
At least that's what I
Well,
experienced.
I've done it in the past and it's worked out okay. So hopefully, Cheyenne, if you have any trouble next week, let me know. All right. If nobody has any questions, we will go ahead and get started with our class today. We have a lot that we want to cover. So make sure that you can see this physical science slide on the screen. If you cannot see it, please let me know now. All right, excellent. One more second. All right, takes me sometimes a minute to get things set up. Okay, so a couple pieces of information, just two this week, so that's pretty good. First of all, just this one is a reminder. When you write to me through Canvas inbox, please give me lots of details. Don't just say something like, the video isn't working in the lesson. I need to know what lesson, which video, where it is, where you find it, all the information that I would need to be able to help you as quickly as I possibly can. All right. And the next piece of information then, and this is really important. Some students have told me that they've been checking on the grades link on the left side of the page to see what assignments they needed to do. So I need to make sure that you don't do this because it doesn't list all of them. I'm going to show you exactly what I'm talking about here. I'll drag in, this is a fake student account that I have here. So see where it says grades right over here? You can use that to check and see how you're doing. You can also use it to see if you missed anything. If you see this little icon that says missing right there, that means you didn't submit it. But don't use it to follow along to make sure that you're doing your assignments because there may be some in this that are not. There may be some missing ones, things that are assignments that don't show up here. And there may be some things show up here that I just haven't deleted yet. If I delete them off of the home page, the modules page, they don't always delete off of here right away. So there's two ways that you can go about finding your assignments. Wick.
Oh yeah, I noticed that I couldn't submit my I couldn't mark that my states of matter 1.5. It's not the quiz, but I couldn't mark it was done.
Probably, usually when that happens, it's because you're in your parents' observer account. So what you
But I
want to do whenever you don't see a way to submit something or mark it as done, log out and then log back in using your username and password. They look the same. So it's kind of hard to tell which is which. But if you log out and then log back in, you should see a place to submit that. If you don't,
yeah,
Wick, please let me know.
for all of the other assignments, so like if it doesn't work, I check these other assignments and I can always submit those. And I even check my account and it says my name on it.
It says your name on it. Okay, well, let me write this down. I take notes of things that I need to check on. So let me write this down and I will get back to you. That it was 1.5, you said?
Yeah, 1.5 states of matter, not the quiz.
Okay. It's possible that I didn't I didn't set that up. AC.
It's fine though, because it's out of 0, so it doesn't really matter that
Right,
much.
right. Yeah, but you want to be able to tell when you finish something. So I usually check those, but I'll double check and be sure. AC. Can't hear you. Still no. Okay, you can type it in the chat box if you can't get your microphone to work. Okay, so let me show you now what you're going to do. Instead of going into grades right here, you're going to click on modules on the left side of the page. It's always there. And then you can collapse them all. And so you just see the headings, or you can expand them all, or you can collapse them all and then just expand 1 or 2 at a time like that. And you're going to start at the top of each unit, and you're going to work your way down. That's the best way. You can also get there by going to the home page and clicking where it says click above for daily assignments. You'll see it goes to exactly the same page. Okay, so AC had the same thing happen. So that's probably a setting then that I didn't check. So I will take care of that after class, probably later this afternoon. Okay, one more thing to show you here. 2 more things actually that I want to show you from this home page. So one is that there's a calendar right here, a course calendar, and it lists some of the assignments. Once again, you don't want to use this alone. Don't use this alone, because sometimes there will be ones listed here that are not actually lessons, and sometimes it doesn't show ones that are due. I highly recommend that what you guys do, instead of going into calendar or grades, click on where it says assignments. Okay, another thing I wanted to show you was this right here where it says click above for class recordings. Now, if you click there, you will see the recordings for our last live classes that we had. So you guys are the Wednesday section, so yours will be in this column. And this is our first class. This is our second class that we had last week. You can either click it here and watch it right in Canvas, or you can click it there and go to YouTube and watch it. But by clicking here, you can even enlarge it and make it big, and you can watch those recordings if you ever miss a class. Now, this is new though. See where it says meeting summary? Click here. Meeting summary will be under all of the recordings from now on. And it is a summary of the lesson as generated by AI. Now, if you see here at the bottom, it says AI generated content may be inaccurate or misleading. That's true. There may be some things in here that AI got wrong, that we talked about a little differently, or that something is wrong. So don't necessarily trust everything. But if you want to remember something like, oh, I know we were talking about thermal energy, but I can't remember what it was talking about, what we said, you can go in here and you can read just this little summary. I think that's a nice feature that they just added to that. Okay, anybody have any questions about any of the content that we, the rules and business that we just talked about? Okay, let's move on then. So you guys are learning about matter this semester. Next semester's energy. First, we learn about matter. And you learned last week that matter is the stuff that everything in the universe is made of. Well, today I want to talk about how we know what we know about matter. After all, it's really small. These molecules, and especially the atoms, are really tiny. How did we find out about them in the first place? So according to the modern version of the elements, the things that we think right now, there are 118 different kinds of atoms in the universe. Think about that. There's only 118. And of those 118, only about 90 of them are naturally occurring in big enough numbers. The rest of them have to be made in a lab or are found in radioactive materials. Now, most of you guys have probably played with Legos before, or you at least know what Legos are. So imagine if all you had were 90 shapes of Legos, and that was it. That was all that you had. Actually, it's not all that they have. There are 3,764 different Lego shapes that are used in sets that you can currently buy for sale right now. 3,764 to make all the Lego structures, but you only have 90 to make all the elements, all the things that we see. Just look around your room for a minute. Look at all the different things there are, the different kinds of material that there are. Now think about everything in your town, and then everything in your country, and then everything in the whole world. Then expand that out to the universe. Everything in the entire universe is made out of only 90 building blocks. And of course, we call those building blocks atoms. So of those atoms, 90 of them are the ones that are naturally occurring. We put all of them, all 118 of them, in this very cool tool that we call the periodic table. Now we're going to learn about the periodic table next week, but I want to take a look at some things about the periodic table now. Wick.
Is the atomic number the amount of protons inside of the atom?
It is, and we're going to talk about that today. Yeah, I'll explain all about that, but you're absolutely right. So let's take a look at this B right in the middle of the page right there. So B stands for boron. Boron is the name of the element. You guys have probably heard of carbon and nitrogen and oxygen. You've certainly heard of helium if you've had a helium balloon. Hydrogen and oxygen make up water. So you've heard of a lot of these. You may not have heard of boron though. Well, boron is the name of the element. The B is the chemical symbol for the element. The atomic number right here is 5, and the atomic mass is 10.811. Now we'll talk about those in just a minute, what all those mean. Well, when you have a group of atoms that are all made of boron, we call that an element. One boron atom is an element. 1,000 boron atoms is an element. The element boron has this atomic number, this atomic mass, this symbol, and this name. Now, a group of hydrogen atoms would be called the element hydrogen. So the atoms of each element are mostly identical to one another, but they're different from anything else. And they go together to make compounds, right? When you have two different elements, the atoms combine to make compounds. But how did we find out about elements like boron and helium and carbon and nitrogen? Well, we often study the work of ancient scientists in order to come to the knowledge that we have now. And sometimes knowing how we got here can help us to understand it a little bit more. So we're going to discuss today how the atomic theory developed. So the atomic theory is the theory that all matter is made up of tiny, indivisible particles called atoms. And a lot of it started with this guy here. So it's helpful to know about him. He lived way back in the 4th and 5th centuries. Now, people have always wanted to know about the Earth. They've always wanted to understand things. But this guy's name, anybody know who that is? Anybody recognize that scientist? If you're taking a history class or you're a history buff, you might. His name is Aristotle, and he described matter as comprised of 4 different elements, not 118, 4. Now, the 4 elements that he thought we had were earth, fire, water, and air. Why do you think people might have thought that? Why do you think that they thought there were 4 elements, water, fire, earth, and air? Any ideas? Well, think about what the world is like. Wick.
I mean, that's the only thing that they could actually see in their time. So they thought those were the only elements.
You're right. You're right about that. So AC, you're sending messages just to me. If you want everybody to be able to see your answers, put everyone in meeting. Click the arrow down. Whenever you guys send a message in a chat, if it has that red letters that say direct message after it, it means that you're only sending to one person, probably your teacher. I think that's how it's set. Okay, so you're right. It was what we see. It's the things that they could see or touch. So things in the world were pretty much dry and hot. That would be fire. Hot and wet, earth. Wet and cold, like water, or cold and dry, like air. So this is what they experienced when they experienced life. So we can kind of understand why they thought that. And they thought that for a very long time. People thought there were 4 elements that made up everything in the universe. Now, there were 2 scientists. Their names were, look at that name, Leucippus and Democritus. And they said that all matter is made of particles. And they called those particles atomos. Sounds like something, right? Sounds like atoms. That's what they called it, atomos. And they said that all the matter in the universe is made up of these particles called atomos. Then, so for a long time, for many centuries, actually, people knew that. They accepted that things were made of atoms. It took a while to get there. It took them a while. People argued back and forth. So it was accepted by some people, not accepted by other people. But then this guy, John Dalton, came around in the 1800s. Long time went by, 1800s, and he showed it. He did some experiments, and his experiments gave us some evidence that the atomic theory was true. So based on his experiments that he did, he put out this theory. This is his theory. Elements are made of tiny particles called atoms. Check. We still believe that today. All atoms of a given element are identical. Check. The atoms of a given element are different from those of any other element. Check. Atoms of one element can combine with atoms of other elements to form compounds. Check. A given compound always has the same relative number and types of atoms. What that means is, like, since water is a compound made of hydrogen and oxygen, 2 hydrogens to 1 oxygen, it's always going to be 2 to 1. We're never going to have 4 hydrogens to 1 oxygen. It's not going to combine that way and still be water. It's not still the same compound. Okay, so those 4 are correct. Now let's look at this one. Atoms are indivisible. That means they cannot be broken down farther in chemical processes. Atoms are not created or destroyed in chemical reactions. Well, we know that's true because of the law of conservation of mass. Things are not created or destroyed. Mass is not. A chemical reaction simply changes the way atoms are grouped together. Okay, so clearly that's not true. We know that we can divide atoms a little bit farther. But everything else that he really assumed was correct. And for the most part, we still accept his theory today. We'll talk about what we mean by atoms not being indivisible when we get to it here now. So in 1897, so guys, that's like really, what, 124 years ago? That's not that long ago. So we haven't known about these things for very long. Well, this guy, this scientist named J.J. Thomson, he discovered that there are smaller particles within the atom, right? Protons, neutrons, and electrons. The first one he discovered was the electron. It was the very first, what we call subatomic particle to be identified. And it was only a little over 100 years ago that this electron was identified. Now, from this, he also said that electrons are what we call fundamental particles. That means a fundamental particle is one that cannot be broken down any farther. It cannot be subdivided. So an atom is not a fundamental particle because it can be subdivided into proton, neutron, and electron. But an electron is a fundamental particle. It cannot be broken down farther. So he got a lot right, but he thought that the positive parts of the atom, the protons, he thought those were evenly distributed all the way around, that they were evenly distributed with the negative electrons. Kind of like a British plum pudding. That's what this is called, where the raisins and the fruit are evenly distributed through the whole thing. So they call this the plum pudding model. Well, we know now that the plum pudding model is not true. We know that the protons and the neutrons are in a clump in the middle of the nucleus. And we know that the electrons are in the electron cloud around the outside. Took this guy, though, to tell us that. This was Ernest Rutherford. And in 1911, he was a scientist in New Zealand, and he discovered that there was a nucleus in the atom, and that nucleus contained the positively charged protons, and that they were not evenly distributed. It was not a plum pudding model. In fact, it was all together in a little clump, a very tiny but very massive clump in the center. So tiny meaning very small, but massive meaning it has a lot of mass to it. So he showed that all those positive charges and almost all of the mass of an atom are located in the nucleus. So we call, because it kind of looks like the way he thought this was he thought it looked a lot like the way the planets go around the Earth, or around the sun, the way the planets go around the sun. So he called this the planetary model. Now, he didn't know exactly where or how the electrons moved around the nucleus. That research came along later with a guy named Niels Bohr. But as they continued developing new models, we got closer and closer to what we think today. Rutherford's model is not all that off. So we learn a lot about it by studying the progression and how people came to the ideas that they do. So here's Niels Bohr. He's next. He came along just 2 years later, and he developed a more detailed model of the atom. He developed a model that showed where the electrons could be found. Now, he said that the electrons are circling in more or less round, like spherical orbits. We know now that's not really true. We know it's a lot more complicated than that, but his model is basically correct, and it's still being used a lot. You'll see his model in books because it is two-dimensional. It's just flat, and it's easy to draw on a page. It's a little harder to draw something in 3 dimensions on a page or to put it in a book. So it's still being used today, his model. Now, for the rest of this week, you guys are going to be learning about the structure of an atom. So I want to talk a little bit about how an atom is constructed today. Again, you're going to go over this in lessons, you know, Monday and Tuesday you had a little bit, and Thursday and Friday you'll have a little bit. But the more times and the more different ways you encounter a topic, the more likely it is to make sense to you, and the more likely you are to remember it. So this is foundational. This knowledge of how an atom is structured, how it's put together, is absolutely critical for you to understand how it works and why it works the way that it does. So I want you to make sure that you encounter this a few times. Okay, so the structure of an atom. First of all, we know that an atom is the smallest particle of an element that can exist alone. Wait a minute, though. I thought there were parts of an atom. There are parts of an atom, but if you get smaller than an atom itself, it's no longer considered part of that element. The only one that is considered part of the element is the atom, because all protons are the same. All neutrons are the same. All electrons are the same. It's just different numbers of them that makes the different elements the way they are and makes them behave differently. So an atom is the smallest particle of an element that can exist alone. There are 2 parts to an atom. What do we call the part in the very center of the atom? Wick.
The nucleus.
The nucleus. Good. And I love the way you pronounce that. So I want you guys to look at this word, nucleus. You will hear people say nucleus. It is not nucleus. The U does not come before the L. It is nucleus. That's one of my my pet peeves, is nucleus or nucleus. So I'm gonna insist on it and correct you, but you won't lose points for it, but just we'll talk about it. So nucleus. The nucleus is in the center of the atom, and the nucleus contains the positively charged protons and the negatively charged neutrons. What goes around the outside of the nucleus? What do we call that area around the outside? Quick.
The electron cloud?
It is, yeah, the electron cloud. So cloud is in parentheses because it's not really a cloud like we think of cloud. It's more an area. It is the area surrounding the nucleus that contains the electrons. All right, so I want to stop for just a minute. I want you guys to understand and marvel at the fact that every single thing in the universe is constructed of these tiny particles called atoms that look more or less like this. What's the difference between them? The number of protons that they have in their nucleus. How do they behave? Depending on what the electrons on the outside do. It's really simple, but extremely complex at the same time. So you can see right here, we've got a proton, a neutron, and an electron. So the proton has a positive charge. That's kind of easy to remember because they both start with P. Protons are positive. Protons have a positive charge. They're in the nucleus. Now they're in the nucleus with the neutrons, which don't have any charge at all. We don't have any charge in the neutrons. So we would say they are a 0. They have a neutral charge, but they're in the nucleus with the protons. Then in that electron cloud on the outside, we have electrons, and they have a negative charge, and they are very, very, very small. They are so small that when we add up the particles to see how much an atom weighs, we don't even add the electrons. We don't even consider them. They're so small. They don't have very much mass at all. So they don't go into the weight of an atom. Wick.
the mass of an electron like 1 divided by 20,000?
Let's just leave for our class, for our purposes, we can just say they are so small, they don't even count. They're insignificant when we're talking about mass. Now, they're not insignificant in behavior because it's the electrons that determine how an atom behaves, but they're so tiny, they're insignificant when it comes to the weight of them or the mass of them. All right, so protons are positive, electrons are negative. In a neutral atom, the number of protons equals the number of electrons. So we have an overall atomic charge of 0. Now think about it. If you have an atom and it has more positives than negatives, the atom would have a positive charge, and that doesn't really happen. Well, we call it something else if it gets a positive charge. We don't call it an atom anymore. If it had more electrons, it would have too much negative in it. So we want a neutral atom. An atom is neutral. An atom has the same number of protons and electrons. In this case, we don't count in this case, we don't count the neutrons because neutrons are neutral. They don't play a role in whether or not it's got a positive or a negative charge. So take a look at this picture right here. This is our example. This is helium. How many protons do you see in the helium nucleus? 2. Yep, you see 2. How many electrons do you see? Yes. So this positive proton cancels out this negative electron. A positive and a negative balance each other. This positive balances out this one. These are neutral to begin with because they're neutrons. So we end up with a neutral atom. Quick.
Wait, helium has an atomic number of 2.
Yes.
Is that because there's 2 protons?
Yes. Yep. And we'll talk about that right now. So now back to the periodic table. So every one of these squares in the periodic table is known as a cell. This is a cell. This is a cell. This is a cell. I think that's a little bit confusing. I wish they'd called it something else because there's a lot of different definitions for cell. Like your body's made up of cells, living things are made up of cells, but they call this the squares in the periodic table are called the cells. So here you can see a cell. This is one of the cells. Well, each cell in the periodic table has a couple things in it. It has an atomic number, it has a symbol, it has atomic mass. Sometimes it'll have a couple other things as well. It may have the name of the element that's in it. But basically, what we want to look at here is this atomic number. So this is the symbol for carbon. C is the symbol for carbon. The atomic number of carbon is 6. We'll talk about mass in a minute. We'll look at that separately. The atomic number tells us how many protons there are in the nucleus. So it is the number of protons that determines the identity of the element. All right, now let's practice. Let's do a couple here. So this is aluminum. Aluminum has 13 protons. So what is aluminum's atomic number?
13.
13. Very good. How many electrons does it have?
13.
13. How many neutrons does it have? Anybody see that in the picture at the end?
14.
14. So remember, it only has to have the same number of protons and electrons for the positive and negative to cancel each other out. Atoms of a particular element have to have the same number of protons. If the proton number changes, it's not that element anymore. But atoms can and often do have different numbers of neutrons. So when an element has different variants with different numbers of neutrons, we don't call them atoms anymore. Now we call them isotopes. So aluminum can have 9 different isotopes. We'll talk about isotopes later. Just understand now, it is always the number of protons that makes an element what it is. If aluminum, let's look at aluminum here. So it's 13 on the periodic table. Let's go back to the periodic table and find number 13 right here, aluminum. If aluminum gained 1 proton, now it would be silicon. It would no longer be aluminum, it would be silicon. If Aluminum lost 1 proton, it would be magnesium with 12. It would no longer be aluminum. It is the number of protons in the nucleus that makes these all the same. And all protons are the same. So all these 90 elements that make up almost all the things that we see in the universe are made of the same 3 basic elements that are all the same. It's just the number of protons that makes them different. Pretty cool. Pretty cool. All right, Wick.
Well, I learned that the body needs like electrons to like for your muscles, or no, some part of the body needs electrons, yeah, to make energy. Well, can't the body like, can you like split electrons from the atom?
Yes. So you're getting into biology here, which is what's called cellular respiration. That's where inside one of the little organelles inside your body cells, any living thing cell, it takes a food molecule, say sugar molecule, it breaks it down and it moves it separates the electrons from those atoms, moves, it's really complicated. It moves them across the cell membrane. And when they rush back through, it creates energy in the form of what ATP, what's called adenosine triphosphate. So yes, those electrons are removed. In fact, it is the removal and the addition and the sharing of electrons that makes atoms behave the way they do. All right, so let's move on. Let's take a look here at neutrons are 14. So right about this one. So this is lithium. What is the atomic number of lithium?
3.
Yes, it is 3. How many protons does lithium have?
3.
How many electrons?
3.
Very good, very good. What about this one? This is copper. What's the atomic number of copper?
29.
29. We can tell because the 29 P stands for protons. There are 29 protons. There are also going to be 29 electrons because if it didn't have the same number of electrons, it wouldn't be an atom anymore. It would be an ion, which we'll talk about, but it can have a different number of neutrons. It can have more, it can have less. These are variants that are called isotopes. Okay, now I want you guys to draw an atom. I told you to bring a piece of paper and something to write with. So I have a whiteboard here that I'm going to use. What I want you to do is pick a number between 3 and 10. Any number, doesn't matter. Now I want you to draw an atom that has that number of protons. So if you pick the 3, you're going to go like 1, 2, 3, and put your pluses in the middle. So I'll do 3. So it's got pluses. Now that's the part of the nucleus. That's the proton part of the nucleus. What else do we know that a nucleus has in it? A nucleus has protons and it also has neutrons. So I have to draw my neutrons. 1, 2, 3. I'm going to say this is just a no variant. This is just one that has the same number of protons and neutrons. Now that's my nucleus. 3 protons, 3 neutrons. Nucleus is complete. And they're very tightly packed together. I mean, in reality, there's some space, but at our level, they're very tightly packed together. Then around the outside, we have this electron cloud. Now we'll draw it in the 2-dimensional Bohr model. We'll learn that it's not 2 dimensions. It's actually 3-dimensional, but we can't draw 3 dimensions. So we'll draw it with the Bohr model right here. All right, so how many electrons is mine going to have? Since I have 3, how many electrons should it have to be an atom? 3. Since it has 3 protons, it has to have 3 electrons. Right there, 1, 2, 3. All right, now whatever one you draw, I want you to find it on the periodic table. We can't see it because of the background. All right, so if you want to hold it up and show everybody, yeah, there you go. Yep, so Wick drew one with 4. He's got 4 protons, 4 electrons on the outside. So Wick, what element did you draw an atom of?
Beryllium?
Beryllium, very good. We know because beryllium has 4 protons and 4 electrons. The protons is what matters. Beryllium has 4 protons. Did anybody draw boron that had 5 protons? What about 6? Anybody have 6? 7? All right, Nyla, what element did you draw?
I drew nitrogen.
Very good. You drew nitrogen. It has 7 protons and then 7 electrons are going to be around the outside in order for it to be a neutral atom. What about 8? Anybody draw 8? 9? 10? Most of you guys drew smaller ones. That's okay. That's okay. Titanium. AC drew titanium. All right. So where's titanium? What is the atomic number of titanium? 22. Okay, but I told you want between 1 and 10, but that's okay. That's okay. You could draw the 22. So let's find 22 on the periodic table right here. Ti is the symbol. Titanium is the name. We have our atomic number here, 22, and our atomic mass is right there, which we're going to talk about right now. First, though, I want you guys to notice something about these symbols. Some of the symbols are only one letter. Y, K, B, C, N, O, F. Some of them, though, are 2 letters. Whenever a chemical symbol has 2 letters, the first one is always capitalized and the second one is always lowercase. Always. So antimony is a big S and a little b. Beryllium is a big T and a little e. Iodine is just 1, it's just an I, so it's capital. If there's only 1, it's capital. If there's 2, first it's capital, second is not. Okay. Now, the atomic number tells you how many what is in the nucleus?
Protons.
Protons, very good. How many protons? It also tells you where it is on the periodic table because, as you can see here, these are placed in order. 1, 2, 3, 4. I'm over here, 5, 6, 7, 8, 9, 10, 11, 12, all the way down to here, 56. Now, from 56, we don't jump to 72. 56, 57, 58, 59, 60. Those are out of order because they would make the periodic table too long. We wouldn't be able to fit it on a page. So they move these down and put them down here, but they're still in order. We still go from 57 in order to 71, and then here we go to 72. In this one, we come 87, 88, 89 is down here, 90 all the way to 103, and then 104, 105. So those go in there, but we make the periodic table this way to make it fit better on a page. Wick.
Is there a reason it's colored this way?
Yes, we'll learn about that next week. Yep, I don't want to go into details about it. They're in groups. Yep, we'll learn about what chemical block. It's right here, this chemical group block. That's going to mean something to us next week. All right, so let's take a look at this chlorine in the middle. Let's zoom in on that and see. Now, the atomic number tells us what the number of protons is. How many protons are in a chlorine nucleus?
17.
17, right. It tells us where it is on the periodic table because they're placed in order. The atomic mass now, let's look at that. So the atomic mass basically tells you what size the atom is. There's more to it than just size, but it tells you how heavy, how much mass there is in this atom. So we calculate the atomic mass by the number of protons and neutrons together. Why don't we count the electrons? Why don't they go into that? They're part of the atom. Wick.
They weigh basically nothing.
They weigh basically nothing. Exactly. So we don't even count them. They're just too small for their size to make any difference at all. So when we look at atomic mass, we're adding together the number of protons with the number of neutrons. Now, it's a little bit complicated to determine atomic mass. You can see it's often a decimal. We've got 35.45, so we're clearly not just adding 17 and 17. So neutrons are a little bit more complicated. We'll get into a little bit with them, but for the most part, we're going to be worrying about protons, which make the element what it is, and electrons, which make it do what it does. Now, Like I said, we'll talk about chemical group block later when we, next week, we'll talk about those. So let's zoom in on a different one, on aluminum. So aluminum, right here is its atomic number, 13. That tells us that there are 13 protons in the nucleus. There are also 13 electrons circling around the outside in that electron cloud. The neutrons in this one are 14. There are 14 neutrons in aluminum. So we want to now look at the atomic number is 13. We want to look at what the mass is. Anybody tell me what the mass is? Atomic mass. Quick.
26.981538.
Yes, very good, very good. Sometimes you'll see it just rounded up to 27, and that's fine. But that is basically how massive one atom is. And since we're really only counting protons and neutrons, it's really how massive one nucleus of aluminum is. So right there, that is our number there. Okay, so find on this periodic table the element that has 6 protons in the nucleus. What is it?
Carbon.
Carbon. Find the one that has 20.
Calcium.
Calcium. How about 36?
Krypton.
Krypton. What is krypton's atomic symbol or chemical symbol?
Kr.
Kr. Uppercase K, lowercase r. Yeah. Now, again, notice that it has an uppercase K, a lowercase r. They all do. What is carbon's atomic mass? Can anybody see that, or is it too small?
12.011.
Yeah, 12.011. Excellent. Now, remember, normally atoms are neutral. Normally atoms have the same number of protons and electrons. Protons are positive, electrons are negative. So normally an atom is going to be neutral. Now, in this picture, there's 4 of each. We have 4. We don't know whether it's the green or the pink because they're not labeled, but there's 4 of each. There's 4 protons and 4 electrons in this nucleus, in this atom. Now, sometimes though, atoms like to give away their electrons. Sometimes they like to accept electrons. The electrons actually leave the atom. We'll learn that when we get to learning about electricity later in the year. Electricity is just the movement of electrons along something, along a wire, through the air. So when an atom either gives away an electron or gains an electron from another atom, we don't call it an atom anymore. It has a different name now. It's called an ion. Quick.
Is potassium an ion?
So potassium can be an ion. Sometimes you'll see like potassium written with a K+. You'll see it
And
that
then
way.
sodium, does it have a minus sometimes?
Sometimes that's when sodium and chloride are joined together to make table salt. Then you'll have the Na, the sodium will be positive, and the Cl will be negative because it gave an electron. One gave one up and the other one gained one. So when an atom gains an electron, like here we have sodium fluoride is what we're going to make. This electron goes from the sodium to the fluoride. Now this sodium has one less electron than it had before. So it's going to have a positive charge. The fluorine is going to have one more electron than it had before. So it's going to have a negative charge. Let's talk about that for a minute. If an atom, picture your atom here, and it's got a certain number of electrons on the outside, and it's balanced, it's even, it's neutral. But now it gives away one of its negatives. What happens to that atom? It's now called an ion, but it gave away a negative. So what is it, Wick?
It's a positive ion?
Yes, it is a positive ion. It gave away one of its negatives. That leaves it more positive. What if one gained an electron from something else? Now it has one more negative than it had before. Wick.
It'd be a negative ion?
It's going to be a negative ion. So in this picture, you can see sodium. It has a chemical symbol Na. Give its electron to fluorine. Now the sodium is positively charged and the fluorine is negatively charged because it has one, no, sodium has one less, fluorine has one more. So they form ions. When an atom gains an electron, it becomes negative. When it loses one, it becomes positive. Now, we have special names for them. We don't just say negative ion or positive ion. We have names for them. The names we use are cation and anion. So, do you guys like cats? Are you positive? So, Nyla, you do? Are you positive that you like cats?
Yes.
Yeah. Wick, are you positive that you don't like cats?
I'm kind of neutral.
Oh, you can't be neutral. You got to take a stand. So either way, whether we like cats or not, we're positive about our feeling about cats. So if you can remember, cat ions are positive because you're positive about the way you feel about cats. So cat ions are positive. So when an atom gives away one of its electrons, it is now a cation. It gave away an electron, leaving it positive. So now it is a positive ion called a cation. If it gains an electron, now it is negatively charged. It is a negative ion called an anion because we are positive about the way we feel about cats. All right, let's do a little practice here. So what is the charge that is on the, so here we have our potassium with the 1+ Wick that you were asking about. So this has a charge of +1, right? Hold on a second. I don't think I have, no, I don't have the answers written. Okay, so this is going to have a charge of +1 right here. Now, how many protons are there in this ion? This is positive, it's a cation. How many protons are there in a positive and a cation of potassium? Wick.
39.
There are 39. So I'm sorry, not 39, no. Look down here at this one.
19.
19, right, 19.
So what's
39 is the
39
atomic
symbol?
mass number.
Oh.
Yeah, it's the atomic mass number. So 39 is the atomic mass. The atomic number is going to be 19. We don't say that because it's a +1, don't say 20, because remember, if it had 20 protons, it would not be potassium anymore. It would have 20. It would be the next one up on the periodic table. Now, there are 18 electrons. How do I know there are 18 electrons?
Because it says 1+, meaning
Right.
that there's one less electron.
Exactly. It gave away one of its electrons. So it has a positive. So instead of having 19, the same number of protons, it has 18. It has fewer. So we know that because of the charge. All right. But what about neutrons? What about our neutrons in this? We have to talk about neutrons for a minute because they're there. Neutrons actually are very important. One of the things that neutrons do is they keep the nucleus stable. If there's too many neutrons in relation to the protons or too few neutrons in relation to the protons, the nucleus becomes very unstable and it can break down. It breaks apart in a process we call radioactive decay. That'll come later in the year where we'll talk about that. Just know that as far as how an element behaves, neutrons don't really figure in. We're not really concerned about them. We use neutrons a lot in nuclear reactions and in research, but as far as the behavior of the atom, doesn't really play a role at all. All right, so we talked about ions. A positively charged ion is called a cation because we're positive about cats. A positively charged ion gave away one of its negative electrons. That's why it's positive, because it gave away a negative. A negatively charged ion got one. It got an electron from somewhere else. So it now has a negative charge to it, and it's called an anion. Wick.
I'm kind of confused. Is there a relationship between the atomic bomb and atoms?
Yeah. Yep.
I see.
Yeah, there absolutely is a relationship. In fact, it is the so are they fission or fusion? I believe that it is the breaking apart of the atom that releases massive amounts of energy. And that's what the atomic bomb is. Massive amounts of energy. That's also what happens in the sun. So in the sun, you know, you have hydrogen and helium. You guys all know that, right? Sun is made of hydrogen and helium. Well, what's the difference between hydrogen and helium? What's the difference between these atoms? Hydrogen and helium. There's really only one difference between hydrogen and helium. Wick?
The atomic number?
Yep. Hydrogen has 1 proton. Helium has 2. What do you think happens if we could slam 2 hydrogens together and get them to stick? What would it be now?
A helium.
Yeah, that would be helium. What do you think it takes to slam 2 hydrogen atoms together? A lot of energy. Where do you find that energy? In a star. The heat in a star causes those 2 hydrogens to slam into each other with such force that they fuse and become 1 helium. Yeah, that happens. That happens on Earth too with other things too. This is a really cool subject, guys. You know, physical science is kind of amazing, and we will continue learning about some of the really remarkable things that happen as these atoms interact with one another. All right, let's wrap this up here because we're about out of time. So I mentioned the word isotope at the beginning. So an isotope is an atom of the same element. So it has the same number of protons, same number of electrons, but it has a different number of neutrons. That's going to have the same atomic number, but because it doesn't have as many or it has more neutrons, it's going to have a different mass number. They have the same number, the same atomic number, the same number on the where they're found on the periodic table, because if they change the number of protons, now they would be a different element. So isotopes are just ones, they are the same element. It's an isotope of aluminum is still aluminum because it still has the same number of protons, but it has a different number of electrons. So its atomic mass number is going to be different. Now those isotopes, they can be, let me add this right here. They have varying number of neutrons. They have different mass numbers because the number of neutrons are different. Isotopes, sometimes they're stable, sometimes they're not. So remember I told you that there has to be a certain number of neutrons that they keep the nucleus together. They keep the nucleus from coming apart. Well, if you have too many or too few, it's unstable. If it's okay, if it's just 1 or 2 more, 1 or 2 less, then it's going to be pretty stable, and it doesn't have the tendency to want to change. They stay stable. Now, most of the ones that we find in nature are pretty stable. Unstable ones are the ones that a lot of times we'll do in a lab, and they undergo what's called radioactive decay, and they change into other elements. So let's take a look at carbon here. Carbon's a good example. So carbon, the element carbon, has 3 isotopes that are found in nature. Carbon-12, which is the normal one. That's where you have the same number of protons, neutrons, and electrons. You also, though, can have carbon-13 and carbon-14. So carbon-13 has 7 neutrons. Carbon-14 has 8 neutrons. Now, these behave a little bit differently. Wick.
Is there a reason why it's called carbon-12? Is like that the amount of like atom or not atoms? The sum
Well,
of
when they have
atomic
isotopes,
particles in the
yes,
nucleus?
yes. When they have when an element has an isotope, we will name it, you know, like carbon-12 because when you add together the protons and the neutrons, you get 12. We call it carbon-13 because when you add together the protons and neutrons, you get 13, 6 and 7. We call it carbon-14 because it's 8 neutrons. So 8 neutrons is still pretty stable. That's not going to, I mean, it's going to decay over time, but it's not going to immediately decay. It's not terribly unstable. Now, most of the elements only have 1 isotope. Well, no, most of them have more than that. Let's see here. There's 26 of them. You can see on this picture here. The ones that are in green, those are the ones that only have 1 isotope. So let's look at them. Beryllium, fluorine, sodium, scantium, magnesium, cobalt, phosphorus, gold, cesium. These right here only have 1 isotope. Now, when you hear the word isotope, just think neutrons. Think more neutrons, less neutrons. It basically is a different form of the same atom. If it had different numbers of protons, it wouldn't be the same atom anymore. Okay, once again, I want to just stop and marvel at the fact that everything in the universe is made up of really just these 90 naturally occurring elements. And what's the difference between one element and another? The number of protons. What makes them interact with one another? The electrons that it has in the outermost electron cloud that it has. It's pretty amazing that we have this wide variety of things in our universe, and there really isn't a lot of difference, you know, between them. Wick.
Wait, if that's the case, can't you just make like can you like make atoms inside of a lab?
So yes, that's what all these are right here. Most of these up above 90. So most of these ones up above 90 from 88 here, let's find the 90 right in here. Most of these have been made in a lab. They put them under conditions that cause those nuclei to slam together and then fuse into one. So yes, they make them in a lab. But what we have to remember is there aren't just 90 things in the universe. All these atoms combine together in different ways. Like, you know, an example would be this is a model of a sugar molecule, glucose, kind of sugar that plants make, one of the kinds that plants make. Well, there's 3 different kinds of elements in this. There's carbon, hydrogen, and oxygen in this, but you can see the carbons are black. So there's 1, 2, 3, 4, 5, there's 6 of them. If I had 5 of them, it would be a completely different molecule. If I had 7, it'd be a completely different molecule. So it's a combination in different ways of all of these different kinds of atoms, of different elements bonding together that gives us all the things that we have in the universe. But when we take them down to their lowest level, they're all made of atoms, and all the atoms are made of protons and neutrons in the nucleus with electrons around the outside. Pretty cool. And we are out of time. So I'm going to have to say goodbye quickly, Wick.
Wait, can't you just make these, like, can you make infinite oxygen then?
I
I mean,
I'll address that. I'm going to address that next time. I'm going to write that down. We'll talk about that next time because it's a little more complicated than that. Okay. And I got another class starting in 3 minutes, so I got to go. All right. Thanks for your questions, everybody. I'll see you next time.
Thank you.
Bye.
Goodbye.
Bye.
Bye.